soap bubbles, we observe that each bubble acquires a spherical shape or an almost spherical shape, irrespective of its size. It's the same with a drop of any liquid, such as a drop of molten wax or oil on water. In all these cases, a force tries to reduce the surface area of the liquid to a minimum. For a given volume of a liquid, the shape that contains the least surface area is a sphere. Force due to surface tension makes a drop or a bubble assume a spherical shape. Consider a liquid, say water, in a beaker. The molecules in the beaker are free to move within the given volume. A liquid stored in a container has a free surface. For a liquid in a container, there are two types of forces of attraction. The first one is the force of attraction between the molecules of the same substance, which is referred to as a cohesive force. The force of attraction between water molecules is a cohesive force. The second one is the force of attraction between the molecules of different substances, which is called an adhesive force. The force of attraction between water molecules and the molecules of the glass container is adhesive. Similarly, the force of attraction between water molecules on the surface and the air molecules surrounding them is adhesive. Cohesive forces are short-range forces. Their magnitude decreases with distance, and they become negligible when the distance between the molecules increases beyond 10 to 15 molecular diameters. Thus, we can assume that these molecular forces act on a given molecule within a sphere with a radius of about 10 to 15 molecular diameters. The sphere within which the molecular forces act on a given molecule is referred to as the sphere of influence. For a molecule that is well inside the liquid, the complete sphere of influence is within the bulk of the liquid. The net force on such a molecule is zero, as it experiences an equal pulling force in all directions. For a molecule close to the surface of the liquid, a part of the sphere of influence lies above the surface. As cohesive forces are greater than adhesive forces between liquid and air molecules, and since there are a greater number of liquid molecules within the sphere of influence than air molecules, there is a net downward force. For a molecule that is on the surface of the liquid, half the sphere of influence lies inside the liquid and the other half in air. There are a greater number of water molecules in the lower half of the sphere of influence than the number of air molecules in the upper half of its sphere of influence. Hence, the molecules experience a net downward force. The molecules coming from the bottom of the liquid to the surface have to overcome this net downward force, and hence have potential energy called surface energy. Hence, all the molecules near the surface and on the surface have greater energy than the molecules deep inside the liquid. The liquid surface tries to contract. That is, it tries to minimize the area to lower the energy of the surface, as this offers great stability. Hence, the liquid surface is in a state of tension and behaves as a stretched elastic membrane. This tension is proportional to the length of an imaginary line along the surface. This force per unit length acting on an imaginary line drawn on the free surface of a liquid is called surface tension. If the magnitude of the force is F, then we define surface tension S of the liquid as S is equal to F by L. Thus, the SI unit of surface tension is Newton per meter and its CGS unit is dyne per centimeter. Hence, 1 Newton per meter is equal to 1000 dynes per centimeter. There are numerous examples available to illustrate surface tension in liquids. Water striders, a species of insect with long legs, float on still water surfaces without drowning, as the water surface acts as a stretched membrane due to surface tension. Now let us derive an expression for the surface energy of a liquid. Consider a U-shaped open wire loop fitted with a wire of length L, connecting ends A and D. This wire, AD, closes the loop and can slide on its arms AB and CD. The closed loop is dipped in a soap solution and taken out to form a thin soap film. Even though the film appears to be thin, it consists of several molecular layers, and hence it has two surfaces enclosing the soap solution between them. Both the film surfaces are in contact with the wire and hence experience force due to surface tension to reduce their area by pulling the wire, AD, parallel to the surfaces. The net force on the wire due to both surfaces is expressed as F is equal to 2S into L, where S is the surface tension of the soap solution. Now, if the wire is slowly pulled through a distance x to increase the area of the film, the minimum force required is 2SL. The total increase in the area of the film is 2 times L into x. Thus, there is some work done by an external force F in stretching the film, and hence there is an increase in the surface energy. The work done by the external force is equal to F into x. On substituting the terms and simplifying, we get W is equal to the product of surface tension and increase in area A of the film. Thus, we can also define surface tension as the work done per unit increase in area of the liquid surface or surface energy per unit increase in the area of the liquid surface. Thus, the unit of surface tension can also be joules per meter square in the SI system and ergs per centimeter square in the CGS system. The surface tension of a liquid decreases with an increase in its temperature. When the temperature of a liquid increases, the kinetic energy of the liquid molecules increase, and this decreases the cohesive forces. The decrease in cohesive forces results in a decrease in surface tension. We learnt earlier that an increase in the temperature of a liquid decreases its surface tension. This is one reason why we soak dirty clothes in warm water in the process of cleaning them. Also, adding detergents to water or applying soap to clothes makes cleaning effective. Detergents also help decrease the surface tension of water. Dirt in clothes includes grease and oily stains. Water does not wet greasy dirt, as the angle of contact of the oil-water pairing is obtuse. Adding detergent to the water solves this problem. The molecules of detergent are hairpin shaped. One end attracts water molecules and the other attracts grease molecules, forming oil-water interfaces. Addition of surfactants or surface active detergents reduces the surface tension of water drastically and hence helps water molecules to penetrate the fabric of clothes and carry away the dirt particles along with them in the flow. This kind of action not only helps in cleaning clothes but also in recovering oil, mineral ores, etc. If the angle of contact is obtuse, that is, more than 90 degrees, the liquid forms droplets on the surface and does not wet the surface. Here, molecules of liquid are more strongly attracted to themselves than to those of a solid. Hence, cohesive forces are stronger than adhesive forces. Therefore, it forms a droplet over the solid and does not wet the solid as in the case of water on a lotus leaf or any oily surface. If the angle of contact is acute, that is, less than 90 degrees, the liquid spreads across the surface and wets it. Here, molecules of the liquid are strongly attracted to molecules of the solid. Hence, adhesive forces are stronger than cohesive forces. Therefore, the liquid spreads across the solid as in the case of water on a glass. If the angle of contact is close to zero, the liquid spreads to the maximum extent. In such a case, it is totally absorbed by the solid as in the case of water on a piece of paper. In our daily lives, this property of liquids is used in products such as wetting and waterproofing agents. In the case of wetting agents such as soaps and detergents, when mixed with other liquids, the angle of contact is acute and hence helps penetrate and wet the solids. On the other hand, in the case of waterproofing agents such as resins and waxes, the angle of contact is obtuse and hence prevents the water seeping into fibers and surfaces on which they are applied. You experience this when you use a raincoat to protect yourself from a downpour. When a liquid comes into contact with a solid, it forms a droplet or spreads and wets the solid. For example, if water falls on a lotus leaf, it forms droplets. However, if a droplet of water falls on a paper, it spreads, gets absorbed completely and wets the paper. Observe a liquid droplet at rest on a flat solid surface. The surface of liquid near the plane of contact with another medium is curved. That is, the surface of liquid makes an angle with the solid. The angle between tangent to the liquid surface at the point of contact and solid surface inside the liquid is defined as angle of contact. It is denoted by theta. The angle of contact, theta, depends on the nature of the liquid and the solid in contact, and the medium that exists above the free surface of the liquid. the angle of contact is fixed for a given set of solids, liquids, and surrounding media, usually air. At any point of contact between a liquid and a solid, there are three interfacial tensions to be considered. One each at each interface, namely liquid air, solid air, liquid solid. These are denoted by SLA, SSA, and SSL respectively. The component of tension SLA along the solid-liquid interface is SLA cos theta and is along the direction of the solid-liquid interface. We observe that at the line of contact, the surface forces between the three media will be in equilibrium. Thus, we can define this relationship as SLA cos theta plus SSL minus SSA is equal to 0, or SLA cos theta plus SSL is equal to SSA. The value of the angle of contact depends on the tensions along the interfaces. If the tension SSL is greater than SLA, the angle is obtuse, and if SSL is less than SLA, the angle is acute. Ever wondered why a drop of water or a soap bubble is spherical or almost spherical in shape? The answer is surface tension. Let us learn how surface tension makes drops, cavities, and bubbles spherical in shape. A drop is a small volume of a liquid bounded completely by a free surface. A bubble has two spherical interfaces, one convex and one concave, separated by a thin layer of liquid. A cavity is formed when a small volume of gas is trapped in a liquid. It is like a bubble surrounded on all sides by a liquid. For a drop of a liquid in air, as it is surrounded by air on its surface, there is surface tension acting on the liquid-air interface, and this tends to minimize the surface area. For any given volume, the surface with minimum energy is the one with the least area. Mathematically, it is proven that for a given volume, a sphere has the least area. Hence, a drop would always tend to take on a spherical shape. It is also due to surface tension that in a spherical drop, the pressure inside is more than the pressure outside. Let us study the pressure inside a drop of a liquid in detail. Consider a spherical drop of liquid of radius r in air. If the drop is small, the effect of gravity on the drop is negligible and the shape of the drop can be assumed to be spherical. O is the center of the sphere and XOX' is the axis of symmetry of the sphere. For convenience, consider a diametric cross-section of ABCD of the drop. This cross-section divides the spherical drop into two hemispheres, ABCDE and ABCDG are the two hemispherical surfaces of the hemispheres formed. The circular surface of the hemispheres touch each other along the circumference of the circle ABCD. Each hemispherical surface pulls the other due to surface tension. Consider that the hemispherical surface ABCDE is in equilibrium. In equilibrium, the forces acting on the surface are as follows. the force on ABCDE due to the surface tension of the surface ABCDG in contact. Let this be F1. The force due to the air outside the surface. Let this be F2. The force due to the liquid inside the surface. Let this be F3. The force due to surface tension acts on all the points of the circle ABCDA. If we consider any small part of the circumference dl of the circle ABCDA, the force due to surface tension on this part is SdL, where S is the surface tension of the liquid. This force, SdL, acts along the axis of the symmetry OX as shown. Hence, the total force F1 due to the surface tension of the liquid on the surface ABCDE is equal to 2 pi rs and acts along OX. Now, let us consider the force due to the air outside the surface ABCDE. If delta A is area of a small part of the surface, the force on the small part due to the outside air is denoted by delta F is equal to P1 into delta A, where P1 is the pressure due to air on the surface. This delta F acts along the radial direction as shown. If the radius through delta A makes an angle theta with the x-axis as shown, the component of force along the x-axis is delta F cos theta, which is equal to P1 delta A cos theta. The term delta A cos theta indicates the projection of delta A along the diametric plane ABCDA. Thus, we can write delta F cos theta as equal to P1 into the projection of delta A on the plane ABCDA. When the components of all the forces P1 delta A acting on the different parts delta A of the hemispherical surface ABCDE are added, we get the resultant force due to the air F2 outside the hemispherical surface. The projection of the area of the hemispherical surface ABCDE on the plane ABCD is equal to the area of the diametric circle ABCD and is equal to pi r square. Thus, the force F2 is equal to P1 into pi r square and acts along OX. Proceeding with the same logic, the force due to the liquid inside the surface ABCDE on the surface is denoted by F3 is equal to P2 into pi r square, where P2 is the pressure just inside the surface of the liquid. The force F3 acts along the direction OX dash. For equilibrium of the hemispherical surface, we need to have F3 is equal to F1 plus F2. Substituting the terms for the forces and simplifying them, we get the difference in the pressure between the inside and outside of the drop as shown. Thus, the excess pressure inside the drop of liquid over the outside of the surface is equal to 2s by r. As the drop of liquid is symmetrical about any diametrical line passing through the drop, the calculation holds good for the entire drop regardless of the position of the hemispheres selected. For a drop of liquid in air, there is liquid in the concave side of the spherical surface, whereas there is air on the convex side. the pressure on the concave side is greater than that on the convex side. Proceeding with the same logic for an air bubble inside a liquid, which is a cavity, there is air on the concave side and liquid on the convex side. Here, the pressure on the concave side, which is due to air on the spherical surface, is greater than the pressure on the convex side, which is due to the liquid on the surface. The excess pressure in this case is also equal to 2S by R, where S is the surface tension of the liquid and R is the radius of the cavity. Now consider a soap bubble in air. The thickness of the bubble is very small and is surrounded by air both inside and outside of the bubble. There are many liquid layers in between the outer and inner layers under microscopic observation. Thus, the bubble has two surface layers, whereas we have the soap solution in between. As the thickness of the bubble is negligible, we consider the radius of the inner and outer spherical surfaces of the bubble to be equal. Let this be R. Let the pressure of the air outside the bubble be P1. The pressure within the solution be P dash and the pressure inside the bubble be P2. Consider the outer surface of the bubble. According to the logic derived earlier, the difference in the pressure between the concave and convex portions of the outer surface is denoted by P dash minus P1 is equal to 2S by R. Let this be equation 1. Similarly, considering the inner surface of the bubble, the difference in the pressure between the concave and the convex portions is also equal to 2S by R. Let this be equation 2. Adding equation 1 and equation 2, we get the difference in the pressure between the inside of the bubble and outside of the bubble. On simplifying, we get the excess of the pressure in the bubble over the outside of the bubble as P2 minus P1 is equal to 4S by R. Thus, the pressure inside a soap bubble is greater than the pressure outside by 4S by R. Consider a capillary tube, that is, a hollow tube with a very narrow bore. The word capilla is Latin and means hair-like. When you dip this capillary tube in a liquid, the liquid rises or falls in the tube. This rise or fall of a liquid in a capillary tube is called capillary action or capillarity. The capillary action of a liquid is a consequence of the surface tension of the liquid and the angle of contact of the liquid with the surface of the tube. The extent of the rise or fall in the liquid in the tube also depends on the diameter of the pore and the density of the liquid. If the angle of contact of the liquid with the surface of the tube is an acute angle, there is a capillary rise. The rise of water in a glass capillary tube is an example of this. The angle of contact for the pair of materials, glass and water, is an acute angle. In the case of the pair of materials, a glass capillary tube in mercury, the angle of contact is an obtuse one, and hence there is a capillary fall. Consider a capillary tube of radius r dipped in a liquid with surface tension S and density ρ. Let the angle of contact between the given liquid and the material of the tube be acute. Hence, as soon as the tube is dipped vertically into the liquid, we observe a rise in the liquid into the capillary tube. As the radius of the tube is very small, the surface of the liquid in the tube is nearly hemispherical. Thus, we find a hemispherical surface of the liquid in the tube, referred to as the concave meniscus. Here, A, B, C, D, E represent the hemispherical surface of the liquid. A, B, C, D, A is the circular periphery of the liquid which is in contact with the inner wall of the capillary tube. The height of the liquid in the capillary tube is considered from the surface of the liquid outside the capillary tube, which is taken as the plane of reference to the lower end of the concave meniscus. Consider the liquid column in the capillary tube to be in equilibrium. Then, the forces acting on the liquid column are the force by the surface of the tube on the surface ABCDE of the liquid. Let this be F1. The force due to the pressure of the air above the surface ABCDE. Let this be F2. The force due to the pressure of the liquid below point G, which is in the same plane as the liquid outside the capillary tube. Let this be F3. Let W be the weight of the liquid in the capillary tube. The surface ABCDE of the liquid in the capillary tube meets the wall of the tube along its circular periphery or radius r. Theta is the angle made by the tangent drawn to the surface of the liquid with the surface of the tube from inside the tube at the point of contact, and hence is the angle of contact. Consider a small part dl of the periphery along which the liquid surface is in contact with the wall of the tube. The liquid surface across this small part pulls the surface of the tube by a force SdL tangentially. According to Newton's third law, there is an equal and opposite force acting on the liquid surface by the surface of the tube. The vertical component of this force is SdL cos theta and its horizontal component is SdL sin theta. The vertical component of the force pulls the liquid in the vertical direction. The total force exerted on the liquid surface by the tube's surface across the contact circle is F1 and is denoted by integral SdL cos theta. As S and cos theta are constants, we get F1 as S cos theta into integral dl. On further simplification, we get F1 equal to 2 pi r S cos theta. This force acts vertically upwards. The horizontal components of the force across different elements over the entire contact circle act in opposite directions, and hence they cancel each other, resulting in zero horizontal force. The force due to the pressure of air above the surface ABCDE, F2, is equal to P into pi r square, where P is the atmospheric pressure. The direction of this force is vertically downwards. The pressure at point G in the tube is also equal to atmospheric pressure, as the point lies in the same horizontal plane as the surface of the liquid outside the capillary tube. Therefore, the force due to the pressure of the liquid below point G, which is F3, is also equal to P into pi r square. But this acts vertically upwards. As the magnitudes of forces F2 and F3 are equal and their directions are opposite to each other, they get cancelled. Now, the weight of the liquid in the capillary tube is the product of its mass m and acceleration due to gravity g, and acts vertically downwards. The mass of the liquid is the product of its density ρ and volume v. The volume of the liquid in the capillary tube is the sum of the volume of the cylindrical portion of the liquid from point G to E and the volume of the liquid in the concave meniscus. The volume of the liquid in the cylindrical portion is pi r square h. The volume of the liquid in the concave meniscus is equal to the volume of the cylinder of height r and radius r minus the volume of the hemisphere of radius r, which is equal to 1/3 pi r cube. Thus, the volume of the liquid V is denoted by the sum of pi r square h and 1/3 pi r cube. Hence, the weight of the liquid in the capillary tube W is denoted by rho pi r square into h plus r by 3 into g. As the liquid is in equilibrium, the total downward force, which is the weight, is equal to the upward force, which is F1. Equating the two and simplifying for height h, we get h equal to 2s cos theta by rho r g minus r by 3. If the radius of the capillary tube is much smaller than h, the term r by 3 can be neglected and the expression for capillary rise becomes h is equal to 2s cos theta by rho rg. If the angle of contact theta is much smaller and close to 0, as in the case of a glass-water interface, we take cos theta equal to 1. Then, the expression for capillary rise becomes h is equal to 2s by rho rg. From the expression, it is clear that the capillary rise of a liquid is inversely proportional to the radius of the pore. We find many examples and applications of capillarity in our daily lives. The root hairs of plants have fine pores in them and hence absorb water from the soil by capillary action. A sponge has fine pores in it and hence sucks in water from a surface through capillary action.